Howdy and welcome back. So we talked briefly about plain text files. I hope you enjoyed that trip down memory lane, and we're going to now transition into binary files. So for the purposes of our discussions from here moving forward, we're going to consider a binary formatted file to simply be one that is not written in plain text. So instead of using character representation where each byte of the file is essentially encodes a character, we could look at the representation of an object in memory and simply transfer those bytes to a file. For instance, do you recall our example of 1122? When we wrote that to a plain text file, we essentially represented it as 4 ASCII characters, 4 bytes. Instead of writing it as a sequence of characters to a file, we could go ahead and just grab its in-memory representation. So the way our program is representing an integer in memory, let's go ahead and use that same representation in the file. And we can see here that in binary, that integer would be represented as 4 bytes as specified here. In fact, and this is where the kind of, coolness of this comes, is that in fact, we could represent any integer in the range of approximately -2 billion to positive 2 billion using only a 4-byte signed integer. So contrast this to plain text. If we wanted to store this very large number in plain text, we'd count out the number of characters and we'd find that there are 10, provided I counted correctly. 10 characters would require 10 bytes of memory to write. However, if we wanted to simply drag and drop that in-memory representation into our file, it would only require 4 bytes. Now think about this over time with many of integer values or other types of objects. Writing out in plain text is going to get expensive in terms of space relatively quickly. Using binary files, we'll be able to mitigate this a little bit. So let's think about how this works. So in our application, so I'm talking about like our in-memory representation of these objects that our programs are interacting with. When interacting with an object in memory, if we want to interact with it, we have to go out to its address and begin interpreting the sequence of bits at that address according to its base type. So if we have something like int I is equal to 7, we're creating an integer object named I. It has an address. It lives there somewhere in the memory allocated to our program. If we'd like to see I, we go to that address and we begin interpreting the sequence of 1s and 0s there according to the base type as an integer. And we'd get back the value of 7. We could go out to that memory. We could go ahead and rewrite something over that if we wanted to assign I the value of 11. What we're going to see here is that we can write this same representation as in memory in our application out to a file in persistent storage in binary format. When a binary format is used for files, we cannot interpret each byte as a character because remember, with the plain text format, every single byte within that file is essentially going to be encoding an ASCII character. If we just write binary to the file, we can't interpret it in the same way. And in fact, we have to understand how that file is represented in order to actually decompose it or deserialize the objects that are residing within it. So instead, we must know the file structure when it comes to binary files and interpret it according to that structure during the deserialization process. This is exactly similar to reading an object in memory with this integer I example, and that we need to know how to interpret the contents of the binary file just like we would the sequence of bits in memory in our application. So just to reinforce this, and you might recall these slides, I presented them, I think, during the first week of class. What does this sequence of bits represent? Well, if we were to interpret it as an integer, we get the value 88. If we were to interpret it, and this is just a single byte, 8 bits, as a character encoded ASCII, we get the character X back. That's what it essentially would map to, 88 integer value. When interpreted as character, maps to the ASCII value of X. If we use that toy floating point that I created for this example, and I remember this is not how things are actually stored in the program in terms of the encoding scheme. But for the purposes here, let's just split this up into sign bit, exponent bit, mantissa. And in this toy floating point format created specifically for this example and others, we'd get the value of 3.5. So what does this sequence of bits presented above represent? Well, the meaning of, and assuming this is in a binary file, the meaning of bits in the file is going to be completely dependent on how we interpret them. We must know the underlying structure of the file and ensure that each byte is interpreted correctly. And this is no different than the memory that's been allocated to our program. We have to be able to go out to addresses and interpret the sequence of bits there according to some sort of base type. So why do we use binary files? Or maybe at this point you're questioning, why do we use plain text files? Well, they both obviously have their place, and we'll see that both plain text and binary files are not without limitations, and we'll eventually get into databases, which will prove extremely powerful to store data that has relationships amongst different entities. But why use binary files? That's where we're currently at. Storing values in binary encoding opposed to text characters tends to use less memory. We showed that. For instance, if we're using the full representation of values for an integer object, we can store this huge range within 4 bytes. Now, this is very different if we were just essentially taking that integer and writing it out to a file as a sequence of characters. And in fact, we'd also have to have white spaces to separate where, say, one field starts and where it ends. Or not even fields, but the actual value stored within it. So speed of access to specific records within a binary file is going to be increased. What we'll see here is because each record, depending on how we write it out, we can write each record, we could serialize each object, say a movie object, with the same representation, which is going to have implications if we want to go out to a file and actually update its value. We'll see that we'll be able to almost interact with some of the contents within a binary file, similar to how we could interact with, say, an object stored at some sort of index in an array. So unlike for a plain text file, we're not going to need to read the majority of a file to find a particular value. Instead, we're going to be able to leverage our understanding of the format of the file. And if we do this properly, and if there's some sort of scheme to our coding, we'll be able to actually jump directly to a specific record within that file. This is going to be similar in kind, as I mentioned before, to accessing the nth element of an array. We simply can calculate an offset into our file because, again, it's just a sequence of binary at this point. We can jump to a specific point in it and then just begin interpreting the bytes according to some sort of type. So with that in mind, let's transition, and we'll go ahead and get into, well, how do I do binary I/O in C++? How do I create binary files? How do I read them in? This will be the subject of the next video in this lesson.